let's jump right into this explainer. Today, we're diving into the super fast, furious, and totally invisible world of chemical kinetics. Picture me as your sports announcer, and we are trackside at the most thrilling event in the universe, the Great Chemistry Race. We're going to watch tiny, microscopic molecules rev their engines and zoom right toward the finish line.
But hey, before we wave that green flag, I have a giant mystery for you. Have you ever wondered why fireworks explode in the sky in just 3 brilliant seconds, but an old iron bicycle left outside takes years and years to rest? I mean, they're both chemical reactions, so why is one like a super fast cheetah and the other like a super slow-moving turtle?
Well, the answer comes down to a really cool science term called chemical kinetics. Chemical kinetics is basically the study of just how fast or how slow a chemical reaction happens. It's literally exactly like having a stopwatch and timing a race. We're just measuring the speed of the molecules to see who wins and who, takes their sweet time.
Now, in chemistry, we don't usually study the super slow turtles, like that rusting iron, because honestly, it takes forever to watch. And we don't really track the super fast cheetahs, like explosions, because they're over before we can even click our stopwatches. Instead, we focus on the middle speed racers. These are moderate reactions, like making ammonia gas, which happen at just the right speed for us to actually study them. So when we time our racers, we actually have 2 different ways to do it. Think about being on a long car trip. You can measure the average speed, which is like timing the whole entire race from the start line all the way to the finish. Or you can measure the instantaneous speed. That's like leaning over and checking the car's speedometer at one exact single second in time. You can know the overall time or the speed right exactly now. Let's picture the start line. At the very beginning of the race, we have lots of starting cars. We call these starting cars reactants. But as the clock ticks, you'll notice these reactant cars start to disappear. Where do they go? Well, they cross the finish line and transform into shiny new cars called products. So as time goes on, the number of starting cars goes way down, and the number of shiny new product cars goes way up.
Section 1. Speed boosts.
Here is exactly how we give our molecules a huge turbo boost. First up, heat it up. Raising the temperature is basically like giving the cars energy drinks. They bounce and zoom way faster. Second, crush it into powder. If you crush a solid into powder, you increase its surface area, meaning a lot more cars can race at the exact same time. Third, use a gas. Gases move way faster than solid chunks because they just have more space to fly around. And fourth, turn on the sunlight. For some special racers, shining a light gives them a magical energy beam to speed right up. But, not all cars are built the same. Meet our 2 types of racers. First, we've got the fast ionic racers. These are like simple, snap-together cars. They easily pop apart and snap together to finish the race lightning fast. Then we have the slow, covalent racers. These are more like complicated puzzle cars. They take a long time to carefully break their puzzle pieces apart and rebuild them into a totally new product. But wait, what if your puzzle car is stuck going super slow? You need a catalyst. A catalyst is the ultimate track secret. It's like a magical shortcut tunnel that gets the cars to the finish line so much quicker. And honestly, the craziest part? The tunnel doesn't actually join the race or get tired. It just gives a faster path for the cars to zoom straight through. Section 2. The secret race rules. We call this molecular rulebook the rate law. The rate law asks a really simple question. If we add way more starting cars to the track, does it actually change the overall speed of the race? You might automatically think that more cars equals a faster race. But in chemistry, the answer is, well, it completely depends on the secret rule for that specific race. Don't worry, these rules are super simple. They're called the order of reaction. If a race is 0 order, it means adding extra cars does absolutely nothing to the speed. The cars just totally ignore each other. If it's a first order race, then if you double the number of cars, the speed of the race doubles too. And if it's second order, adding more cars gives a super speed boost, making the race 4 times faster. It's really just simple cause and effect. Section 3. One step or many? So, some chemical reactions are just one quick single step. We call these elementary reactions. It's like a straight drag race from start to finish. Zoom, and it's done. But other reactions are complex. That means they take multiple steps, kind of like baking a cake. First you mix, then you bake, then you frost. It's a multi-lap race with a whole bunch of pit stops along the way. So, if a complex race has 3 different laps, how do we know the final time? Well, here is the golden rule of the track. The slowest step completely decides the winning time. Just imagine a relay race where one runner is super fast, but the other runner stops to tie their shoes for 5 minutes. The whole team's time is totally ruined by that one slow pit stop. In chemistry, that slow step is the absolute boss of the clock.
Section 4. The bumping cars game.
This wild bumper car game is called molecularity. Molecularity is really just counting the number of tiny reactant cars that must smash into each other perfectly at the exact same fraction of a second to transform into a winning product. Sometimes one car just bumps a wall. Sometimes two cars bump into each other. But get this, the absolute limit is usually the number 3. It is super, super rare for more than 3 bumper cars to hit each other perfectly at the exact same time. Just try to imagine 4 or 5 cars all crashing together at the exact same perfect angle. It's almost impossible. So the big rule of molecularity is that it's almost never higher than 3. And here is exactly why it's so hard. It's all about effective collisions. You see, just bumping into each other isn't enough to win the game. If the cars tap each other softly, nothing happens. If they hit each other backwards, nope, nothing happens. To win, the tiny molecular cars need to crash at the perfect angle with the perfect amount of super high energy. Only then do they actually transform into products. This microscopic world is clearly full of rules. But wait, can a chemical reaction trick us? Like, can a reaction actually put on a disguise and pretend to be something it's entirely not? Actually, yes, it can. Meet the ultimate trickster of our track, the pseudo-first-order reaction. Pseudo is a funny word that basically means fake or acting in disguise. This is a sneaky reaction that looks really complicated on the outside. It totally pretends to be a big, difficult 2-car race, but when we look closely at the math, it acts as simple as a 1-car race. So how does it pull off this magic trick? Well, sometimes in a race between 2 things, one of the reactants is incredibly huge, like a giant ocean of water. Because there's so much water, a few tiny drops splashing out doesn't change the ocean at all. Since the giant water reactant basically doesn't change, it doesn't affect the speed of our race one bit. So the judges just completely ignore it in the rules. Sneaky, right?
Let's look at this awesome quote to wrap things up. Every chemical reaction is a race. Sometimes you just need the right speed boost. Whether it's zooming around with a catalyst shortcut or bumping perfectly as a gas, these tiny molecules are always on the move, literally transforming our entire world.
So, my fellow scientists, what secret shortcut will you use in your next big chemistry race? Are you going to heat things up, crush them into powder, or maybe find a magical catalyst? Keep your eyes open because the amazing race of science is happening all around you, every single second. Keep exploring and keep racing.